Good morning, Gabriel. How are you?
Good.
That's good to hear. How's the semester going?
Good. It's going fun.
Nice. Morning, Calvin. How are you?
Doing pretty well.
It's good to hear. Is your
So,
Oh, sorry, go ahead. I was just gonna say, is your room very long and narrow, or is it the camera that makes it look that way?
it's longer.
Interesting.
Uh, where the testing center is at ISU, I've never used it before.
Oh, let's see.
I was trying to look it up online, but I could never find an actual building.
That is a good question. Hmm. I kind of think it might be like in or near the library, but I don't actually know if that's true or not. So this is actually on my list of stuff to figure out because so I'll have more I'll have more information next week about that.
Okay. Yeah, because I was looked it up online and I was like reading what I would have to do and like I think I was reading that you have to like schedule an appointment and everything.
Yeah, and I think I actually am supposed to schedule it for you. So I need to they have forms on there. But they don't. Yeah, anyways, I was looking at the forms a week or a couple weeks back and I was like, I need to call them again because what the yeah, anyways. So I'll yeah, there it was I was a little confused as well because I had initially called them and they gave me some information and then I looked and then they said, yeah, just fill out the forms, and then the forms didn't look like what they said. So I'll double check. Not necessarily an uncommon situation at ISU, as you probably have learned over the last few years. Um, but I'll figure it out and figure out where it is as well. Yeah. So contact us. Maybe that it's under there. Oh yeah. Okay. Actually, here it is. It's in Gravely Hall. So what is that? One past the admin building if you're walking towards the P sub from engineering, I think. Let me check. Yeah, so it is, yeah, it's like just past the like if you're walking, from engineering over to the student union, it's that one that's just past the administration building, somewhere in there.
Okay.
See if I
Pretty simple then. Okay.
street view this or whatever. So, right. Let's see, here's the, you're in the quad, engineering is like right over here. And there's the admin building, it's somewhere in here.
Okay, that'll be pretty easy to
Yeah.
find then.
Yeah, so somewhere in that building, it said it's on the 3rd floor, but that building looks like it might be, kind of have multiple wings. So I bet you when you get inside, there's some signs that say where that, which wing or something that's on, but Gravely Hall South. Okay, actually, so that would be, oh no, I don't know. It's somewhere on the 3rd floor. I don't know if it's on this side or this side, which one they consider south. I think it's probably this side is the south side. Ooh. Interesting. Sorry, now I'm just playing around with Google. Okay. So looks like, well, a few minutes after 8. Looks like this might be everyone for today. Not a huge group. So let's see here. As we were just discussing, the exam is next week. I will have more information about the testing center, how the test will go, where it will be, etc. I am actually also going to be in Pocatello today, so I'll probably just walk over and ask them in person, but that also means if you are in the engineering front office and my door is open, feel free to stop by if you happen to be there. I know I have a few meetings throughout the day, but if you see me around, feel free to say hi. My office is right next to Dr. Stuffles, so if you know where his office is, mine is right next to his. I added, so based on what we talked about last week, I added another cookbook that describes how to find the electric scalar potential, so the voltage due to distributed charge sources. So I added that up there. So if you want to take a look, it's in many ways, it is similar to the Gauss's law cookbook, right? So I just put it down here, electric scalar potential cookbook. And this basically, you could use this to get to these 4 expressions, which these are the ones that are all included in the textbook. So these are the expressions the textbook gets. And this just helps you figure out for your problem how to arrive at this expression.
I don't think you're on your on the web right now. I don't think it's weird.
Oh, I see. I know. I think I know what's going on. Thank you. 1 second. Here we go. Okay. So it's just under, it's this electric scalar potential. These are the 4 expressions in the cookbook for voltage, point, line, surface, volume. And I just made the steps to help you realize, okay, this is how you get to that magnitude. And that's just like the problem we did in class. Now, we also have, so I also posted up here. Let's see, I'll make it look like what you should see. No. Okay, so you should see this also now on your Moodle. These aren't due or required, but they're just a few more random questions that you can use to practice the various things we've learned. So feel free to take a look at these. I will post some of the solutions for these, maybe all of them, like either after the weekend sometime. So I'll give you the weekend to look at these. Next week on Tuesday is a review day before the exam. So on the review day, right, it's basically up to you all to ask questions. Like we'll just go as long as you have questions. So if you have no questions, then we'll end. If you keep having questions, then we can keep going. So I think of these as something that might help you come up with questions to help you understand what's going on with the course, but they're definitely not, these are not required. They're all optional, more practice. So that is on the Moodle page under this important document. So it's kind of close to the top, one of the sort of top things. Okay. Does anyone have any questions? All right, next Tuesday, we'll have the quiz. The homework will be submitted, then we'll review. And then on Thursday, we'll have the exam. So if you do think of any questions actually, let me rephrase that. Do think of questions and bring them next Tuesday. And that's when we'll be reviewing. All right, so let's finish up homework 4. What problem would you like to look at next?
Can we look at question 5?
Yeah.
Basically more about the conductivity portion. I really forgot how to do those.
Okay. All right, so this one, this problem, we only have a couple problems in here, but basically the reason behind this problem, and you may have you seen this? Did you do problems like this maybe in 3329? Like a microelectronics class?
I mean, yeah, I did some of these.
Okay, sure. So I'm not saying, oh, you have to remember this. I'm trying to, what I'm going for here is trying to make a connection, and that connection is something similar to what we looked at with the voltage, which is, right, I think probably up until this point, if you're like me, you probably approached these electrical engineering classes from this like very circuit-based perspective, right? Like you have these large things, like you have a battery in your thing, you have a capacitor. There are these discrete components that they're separated from each other. In your microelectronics, that was probably the first time when you were pushed to think a little bit more about, okay, these are all integrated together, right? Like the very structure of a microelectronic device, like the very structure of a MOSFET means that it has capacitance somewhere, right? Like and that's what the real world is like. It's actually, you have these things that are very closely integrated. And then where this course comes in, which is probably a bit different than like your microelectronics or your circuits classes, we're going back even further, and we're approaching this from like a physics or a field theory perspective, where we're looking at things like if you have a bunch of current flowing in a semiconductor, right, that current is moving charge, and if the current is moving at a steady state, right, you're going to have fields that are associated with that. And so there's another way to approach those microelectronics problems that is from the perspective of them being more of like a field theory, rather than looking at them and analyzing them more like the Kirchhoff's law. And you will, of course, if you simplify the problem or make the right assumptions, right, you'll end up at the same result. But the idea with this problem and some of the things that you see in these other classes is to make these connections between how the physics works and then how to solve those discrete circuits that are usually, one of the first things that electrical engineers learn. So it gives you some information about a cylindrical bar of silicon. So you have a radius, a length, and then you have a voltage, and then these describe how easy it is for the electrons and the holes to move in that silicon, right? So this is a coefficient that describes how easy it is for them to move in that material. And then this number, right, is I guess you could think of this as a density, like a charge density, or like a number of electrons you have per volume. And then it's saying that the number of holes and the number of electrons are equal. So you have some information about how many electrons are in your material. You have some information about how easy it is for them to move. And then you also have some information about the voltage that's applied. And when you apply that voltage, right, that's like a potential. So this is like gravity. So it's going to tell you what the potential difference is between the beginning and the end, or something, some two areas on your on this cylindrical bar are. Okay. So the conductivity, that is a equation that's in the textbook. Okay. So it should, in that textbook, you should find a equation like this. Okay. Right, so the conductivity, right, this is the electrons, and then this is the proportionality constant, and then this should be the charge of a single electron. Okay. Do you remember what the charge of a single electron is?
I know it's times 10 to the -16th, but
yeah, let's double check that. This 16 might be a some constants in here. 16, I think, might be a different unit than is normally used. Okay. Thought maybe it would say in here. I think it's, I'm not sure what units yours are in, and I'm trying to remember, but I think it should be times 10 to the minus 19th. I guess I should just look this up. All right. Okay, yeah, 1.6 to the minus 19th coulomb. So your number might have been in microcoulombs or something. Okay. All right, so you should have enough information for this. So on your piece of paper, see if you can come up with the result for this conductivity of silicon. All right. Has anyone got an answer yet?
Yeah, I have an answer.
All right. What did you get for the answer?
I got 4.32 times 10 to the negative fourth.
Yeah, that should be correct. Okay, now, yeah, one other thing, right, I was going to note, so that is correct, and right, the reason, right, we can go between these two is, right, we have this, this current, right, current is a description of, that's moving charges, okay? So current is,
Quick question, Dr.
yeah,
Professor.
go ahead.
I got 0.432. I don't know if I was supposed to make a conversion, which
Perhaps, let's see here. What was your times 10 to the what?
didn't get the times 10. I just had 0.43. So I don't know if I was supposed to make a conversion somewhere.
I don't think any of these actually needed to be converted. So there might have been just a small math mistake. I'm not sure.
You can go ahead. I'll try and figure it out.
Okay. Yeah, anyways, so it's probably just a small math mistake. If the reason, so when you're thinking about this problem, right, the reason that we can use this to find the conductivity, right, is the conductivity is a relationship between the current density and the electric field, right? So that you could almost think of the conductivity as a proportionality between these two, right? So if we have a current density, right? So this is a current density field, then it's proportional to the electric field by this conductivity. In current density, right, we should guess that this has something to do with how easily, right, the electrons move. And you can write the full current density as the electron, the movement of the electrons, plus the movement of the holes. So one will be probably in one direction and one in the other direction, but it'll be the summation of the movement, which you could write as, right, the density of the electrons multiplied by the velocity that they move in. So this is a velocity plus the density of the holes and the velocity that the holes move in. Now these numbers, right, the holes and electrons, they move at some velocity, and that velocity, so for the electron, the velocity is also proportional to the electric field. So this kind of makes sense, right? Like you might expect, right, if you apply a potential between one side and the other, and then you put something that reacts to the potential inside of this field of potential, there will be some energy associated, like there will be a, if you don't do anything, right, that thing would move in the field that it is related to, that it has the potential to move in, and it will move at some speed. And these things are proportionality, right, to how reactive an electron is to a field. And that's why we can write the conductivity. So the conductivity is basically a proportionality between the current and the electric field. So the current field and the electric field have a proportionality of the conductivity. And the conductivity can be thought of as also be thought of as a relationship between how fast do electrons and holes, how fast do they move when they are inside of that potential. Okay, does that make sense? Is that even helpful?
Yeah, that makes sense.
Yeah.
Okay, so this is kind of like just another way to think about these things. Normally, we're used to just, getting this number, but we could go down to those physics principles and think about it the same way, or in a similar way. And that's, sometimes you do that in microelectronics, sometimes you do that in electromagnetics. Pretty much anytime you're looking at things on like that micro scale, not as a discrete device, but as an integrated device, it may be convenient to think about it this way. So the next question is about current. And this is kind of simplifying current from a surface or volume current into a current like the way that you normally deal with it. Okay, so then your current could be equal to a surface current or a volume current multiplied by an area. Okay, so if J has units of amps per meter squared, and you multiply it by area, which has units of meter squared, then you'll get to current, which is how we typically have dealt with it in our other circuit classes. And from what I was just telling you as well, right, we could think of this this current. So this surface current, which is a current that's along a surface. So we give it this units of amps per meter squared. We can think of it as this being equal to this proportionality with the electric field. So we could also write by substitution this, and electric fields, right, they have units of volts per meter squared. So if we know volts per meter, apologies, right? So the volts, right, we were given 5 volts. And here, right, we were told how long that this cylindrical bar is. 8 centimeters. So we can come up with the electric field strength by the voltage we were given and the distance. And do note here, right, we're being a little, because this is, probably the first time we've looked in detail at this, and also we're going between like a real case and the field theory that we just looked at. We're being a little fast and loose, right, with the difference between the vectors and the scalars. And that is because, right, this could be a vector field, but we are assuming, right, we're assuming based on this problem that the field is in one direction. Okay. And so that basically means, right, if we have our normal electric field and we assume it's in one direction, we could just say that it's EX. And then if our cylindrical bar, right, this is our cylindrical bar of silicon, if this is in the X direction, we're just saying we've converted it to a scalar almost like this. And so we could think of this e to the X field strength, right, where this is the magnitude in the X direction. Does this make sense how we converted from vectors to scalars and kind of in this sort of tricky fashion?
Yeah, that makes sense. But I have a question. So like when you talk an area, are you just mean like a cross section of
Yeah.
the disk? Okay.
Yeah, so the electric field, right, is in volts per meter, right? So this is along the length. And then the current is the surface current. And so that surface current, right, is coming through here. And so this is like charges per area. Okay, and that's where this comes from, this area. So this is the area here. And this is the amps. So looking at the current in this way for like a physical object, the potential is along that length direction, right? We've applied a field. Somehow there's a potential from here to here. So our E field is pointed right in this direction, and being the E field being pointed in this direction. Let's see. Is that correct direction? It gets a little confusing because electrons are, yeah, okay, I think this is correct. But our E field is pointed in that X direction. The which we can describe as a voltage, right? So if we have that E field pointed down our tube, our semiconductor tube, then we're used to, in our circuits classes, we're used to saying, well, we don't care about the E field. We're just going to say we know that there's a potential difference between the two. And the potential difference came from the field strength. So there's some field strength that makes potential difference. It's 5, which is 5 volts along here. And that potential difference caused the electrons in the holes to start moving inside of this bar of silicon. And because it's not an infinitely thin wire, but this is actually some tube, or it's a real volume of material, the charges are moving. They can move around anywhere in this. But in the end, right, it's often useful because we want to be able to work in 2 ways. We want to be able to understand, one, that yes, the electrons move due to the field, but also it's very convenient for us to express it in terms of a single current as if it were infinitely thin, because that's what we're used to dealing with. And this will make our, just like this is why you start in circuits 101 with the discrete components. We're used to dealing with things as if the wire is infinitely thin. And that's what this I says. Let's just imagine the wire is infinitely thin. All right, so does that make sense? Can you find the current now?
Yeah, that makes sense.
Yeah. Should take just a moment if you want to find the current. Now, to Daniel's point earlier, you should, I believe we had centimeters here. We had millimeters here and centimeters here. So do be careful on this one that you must.
Yeah, I figured that was what was wrong.
Yeah. So go ahead and find this and then be careful because you will need to convert your 8 centimeters to meters, and you should convert your, what is this? 4 millimeter radius. You should convert that to meters as well. So go ahead and take a moment, find that answer. All right, anyone get an answer? Need a few more minutes?
Yeah,
All right, what did you get, Cade?
I got 1.36 microamps.
Yeah, that should be correct.
Wait.
Yeah. And then typically you would express this right in terms of microamps. And so when you were probably you did this in your 3329 class, but in microelectronics, they usually avoid using this this type of SI notation or this type of notation when they can in favor of these SI units, especially for things like current or yeah, especially for current. So that is why the answer would be in microamps, or would be preferred in microamps. And then the very last part, right, is we have R equals V over I, right? And so this is just, we have now basically converted our three-dimensional material into a simple problem like the ones you saw in your circuits classes, right? And so we just started with Ohm's law, and you can calculate the overall resistance here. So I'll give you another minute or two to find this resistance. Let me know when you've found it.
Found it.
All right, what did you get?
3.68 mega ohms.
All right, that sounds correct to me. Okay, so this problem, yeah, hopefully you have a better understanding of it now. Basically converting some microelectronics ideas, some field theory ideas, into converting them into something that's more one-dimensional and familiar to the things we've seen in our other circuits classes. So just another look at this. If you end up working in semiconductors or something, this type of thing is something you might look at a lot. But if you end up dealing, if you design larger circuits, right, maybe like PCB boards or something, you may not look at this quite as often. So just good to be aware that it exists. All right, what other homework questions do you have? I mean, really, we only have these boundary condition ones left. So what do we need to do to find E1 here? We have E2. What should we do to find E1? Right, so these are going to have a relationship to each other. These two materials have different dielectrics. The boundary has a surface charge. So how can we find E1? What strategy should we use?
A formula for it.
Yeah, there is a formula, and we should also and that one of those formulas, right, it tells us a couple things. Right, one formula for the electric fields tells us that E1 tangent is equal to E2 tangent, right? So this is one of the boundary conditions. And the other boundary condition, right, tells us that the field density are also related, right, to the total charge. So this one, right, this tells us about the tangent. And this one tells us about the normal. See, so let's see, one other thing that we should recall that's always true. This is not a boundary condition, but just something useful. Always, this is always true. Is, right, that the electric field, an electric field is equal to the sum of the tangent part of the field and the normal field. So the full vector field, right, the full vector field is equal to the sum of the tangent vector field and the normal vector field. All right, so what is at this surface? So we have this surface, right? This is the boundary. What is the normal? What is n? For this boundary, what is n?
It's Z.
Yeah, and how did you know that?
Normal is perpendicular to the direction.
Yeah, so the boundary is on the xy plane. So the normal part must be in the z direction, right? Okay. All right, so see if you can figure out using the first one, right? We now know that that must mean that the tangent, so if the normal is in the z, then the tangent is x and y. So see if you can find, we're trying to find E. We know that the E1, right? So we know that E1 would be equal to E1 tangent plus E1 normal. So if we can find, we could find that first, we could use these two boundary conditions. First, we could find the tangent part, and then we could find the normal part. So first, see if you can figure out what the tangent is going to be. So figure out what E1 tangent is. Let me know when you have an answer. All right, so what is E1 tangent? Let's see here. So, Gabriel, is this part of, is 3 in the x direction? Is this part of the tangent field? Yes or no? So we said that the tangent, we said that the normal is in the z, the tangent is x and y. So what was your answer? Yes or no? Yes. All right. Yes, I agree. So that's part of the tangent field. And Cade, is this y? Is this part of the tangent field? Yes or no?
Yes.
Yeah, I agree. And AK, how about you? Is this z? Is this part of the tangent field? Yes or no?
Yes.
All right, so we said the tangent field has x component and y component, and the normal is in the z. So
And I believe it's not.
yeah, that one's not actually part of it. So okay, we're on the right track now, right? We have the tangent field, and remember, so now we know what E1 tangent is, and we can find all of E1 by finding E1 tangent plus E1 normal. Okay, so we just found this. Now let's move on and apply our second boundary condition. Okay, actually. Okay, so we already said n is z hat. And then we also know that we could write, we have a relationship like this. All right, so we could rewrite this as E1 minus E2. Oops. Sorry, this should be the surface condition. Let me change that here. Okay. Oh, and I forgot one other thing. What does anyone see what I forgot? It looks minor, but it's actually serious. Right, I forgot that this is the dot product, right? Because when we take, we're trying to find, we're going to want to find a scalar value. So we need to remember that. Now, is this commutative? Can we write this as z hat? Let's see. Is this okay?
Yep.
Yeah, it is okay. Okay, so now see if you can find, right? We're trying to solve for something. What are we trying to solve for?
E1.
Yeah, we're trying to solve for E1. And after we do this operation, if I take z hat dotted with E1, what are we going to get, Daniel? What is the result of this?
Is scalar.
Yeah, but if we, so this is saying, right, E1, right, this is really saying, um, right? So what is this equal to? You said it was a scalar, which is correct. And then what are the variables going to be?
We just have X and Y.
So z hat dot with this, does it stay there or go away? Are we going to have any X direction?
Oh, go away.
Yeah, it'll go. Those ones will go away. X and Y will go away. Z will stay. Right, so the solution, right, is E1, and I guess I should probably E1 Z. Okay. And so what is this going to be? What is the result of this going to be? If I take Z hat dot with epsilon 2, E field 2.
Also E2, E2Z.
Yes, that is absolutely correct. And this is another scalar. Okay. And what is E2 Z equal to? What is the number? Let's see. Calvin, you got it?
Yeah, it's just 2.
Yeah, right. This was the part, right? This is the normal part, right? Okay. So it's 2. So we can just go here and plug that in. Then we also have this information from before. Oops. Should go here. All right, and do you remember what we're trying to solve for now? Right, we've looked at the boundary condition. What are we trying to solve for in here?
I'm trying to solve for E1 right now.
Yeah, E1, and then which, does it have a directional component that we're also trying to solve for? Yeah, Z, right? E1 Z, that's what we're trying to get. Okay, so it looks like now, let's take a look at this. Do we know what epsilon 1 is? Yes or no? Do we know it?
Yeah, we do.
Yep. Do we know E1Z? No, right? We're trying to solve for this. Right? This is what we're solving for. Do we know epsilon 2?
Yeah, we do.
We know that one. We know this. And we know this. So that should be enough information, right, to solve for this part of the field component, right? And once we do that, we'll put it in here. And then we'll get the full electric field 1. All right, so let's not forget where we started from. We said, we know this field, we know field E2. We think, okay, man, there's got to be a relationship between E2 and E1, and there is. The relationship is between the boundary conditions. We have 2 boundary conditions. One's tangent, one's normal. The tangent one was quite easy to do, right? We were able to determine, let's look at E2. We know what the full E2 field is. We can find the E2 tangent. That'll be equal to the E1 tangent. So we did that, and that was quick. And that was the first half of solving for electric field 1, which is the full field we're interested in. So we broke it into parts. We did the first part using the first boundary condition. Now we're on the second part with the second boundary condition. The second boundary condition is between the normal parts. We had this equation. We figured out what the variables were that we were interested in and what we would need to solve for. And now we're here. So we need to solve for E1Z, which is E1 normal. And then that's going to give us the full field. So on your paper now, you should be able to take the information you know here and use that to solve for this E1Z, which is the last remaining part of the E1 field that we're trying to find. So go ahead and work on that on your paper. And let me know when you have an answer.
You're just looking for the Z component, right?
Yep. Yeah, so we know epsilon 1, epsilon 2, E2Z, and we know the surface charge density. So we just need to find this E1Z.
I got 1.11.
Yep. I think that is also the answer that I got. So let's write that down here. All right. All right, so the full E1 that I got then is in the X direction 3 minus Y2, and then in the Z direction 1.11. Okay, now, does anyone have any questions about how we applied those boundary conditions? All right, in that case, let's keep going. Let's figure out what this angle is, okay? So what angle does E2 make with this axis? There are a couple ways that you could solve for this, but recall, we say that the product of A and B is equal to the magnitude of A and B cosine of the angle. Now, if we said A, we could say A is E2. And B is Z hat. So the portion of E2 in the direction of Z, we could solve for this and this would give us E2Z E2 cosine theta. There's probably some other ways of doing this as well. But this is one of them. All right, so I'll give you a minute to, let's see. I'll let you solve for this on your own later. I want to give a couple notes about the last one. You could, of course, do some other, you could use some other trigonometry, but this is kind of a vector way to solve for this part, this angle. Okay, so we should take a look at this very last problem just for a moment. Right, the very last problem is about a cylindrical system, infinitely long cylinder with infinitely long conducting cylinder with a surface charge density. The surface is surrounded by a dielectric that contains no free charges. So the dielectric has no charge density. Okay. And so we're defining Z hat as the axis of a conducting cylinder. All right. So we've defined this. We have a conducting cylinder. A couple things to note. What is on the surface of this cylinder here? What is the normal to that surface? What's normal to the cylinder, the way we've defined it?
It'd be R and V, wouldn't it? Some component R and V.
All right, so you're close. The normal on the surface of the cylinder, there will because it's a cylinder in cylindrical coordinates, we'll only have one directional component. Right. So even on this side, the normal will be the same direction. So you said R hat and phi hat, and it's actually just one of those. So do you know which one it is?
Well, I would say I have to say R then.
Yeah, exactly. So the R hat is normal all around here. Now right, we have two different places where we should, or a couple different things that we should think of, but when we have, when we're looking at boundary conditions, let me see if I can paste this in. I think there's something that says it, but when we're looking at boundary conditions, there is no electric field at the surface, or at the surface of the conductor. The electric field 2 is going to be equal to 0, and that is one of the boundary conditions. Okay, here it is. Yeah, so for this case, right, we do have one medium, right? In the first problem, in problem 6, we were looking at a case where we had two media. One of them, both of them were dielectric, but this case, problem 7 is different, right? We have one medium that's a dielectric and one that's a conductor. So on that dielectric conductor boundary, right, there's not actually any field. Okay. But because this has an inner conductor and an outer conductor and a dielectric, you will need to consider using both of these. Okay, so you'll also have to use the normal field condition. All right, I don't want to give too much more away than that. And plus we're about out of time, but just know that these conditions are the ones where you have dielectric 1 and a conductor. We'll be using those in problem 7, and you've now determined that the normal is in the radial direction. If you have any questions, feel free to stick around. If not, I will see you all next week, and I'll have more information next week about what the exam is going to look like, and bring your questions for the review. So,
Okay, thank you.
yep.
So are we writing the exam in the writing center, the
Yep.
testing center?
Yeah.
And what can we take to the exam?
You can take 1 page of notes. Yeah. So all the cookbooks will be printed into the exam by the testing center.
Oh, okay.
Yeah.
So this last problem we solved also, I don't know if my values were wrong, but I can't. So the value for E2Z, I'm sorry, E1 and E2 is epsilon multiplied by a number, right?
Let's see. Yeah, the last one, you're in the last part of the problem, you are solving for the surface charge density at the surface of the conducting cylinder.
I thought we're
Yeah.
looking for E1.
Yeah, and you won't actually get to a numerical answer. So you'll have because you don't actually know the radius of this cylinder. So your answer will have some variables in it.
I'm asking about number 6, not the last one you were talking about.
Yeah. The infinitely long conducting cylinder? Or
No,
boundary conditions?
the boundary conditions.
Oh, okay, I'm sorry. On A or B?
I think I don't know what part where we had to find E1. I think it was the second part.
Okay. Yeah, I'm sorry. So your question was,
My question was, I'm having trouble with the computation for it. After I substituted the value of E1 and E2 in the equation and solving for it, I can't get the answer because it's either it blows up or it's 0 according to what I have here.
Okay. Yeah, let's look at that just for one more second then. And then we know that E2 is 18 E naught. And we know that E1 is 2 times E2. With me so far on this?
Yes.
Okay. All right, so
We know the value for E2Z too, right?
yep, yeah, and this
That's 2.
is 2. And we also know the value for this 3.54 to the minus 11th. All right, so maybe break this down. And find
Oh,
yeah.
So this is the computation we use, right? This
Yep.
is how we get the answer, right?
Yeah.
I think my issue with this was my sign.
Okay.
I use a subtract instead of addition.
All right, yeah, I got it. And it makes sense, right? This is almost equal to this.
Yeah.
So we should expect it to be very close to 1. Yeah.
Sorry.
No worries.
Okay. Thanks.
A lot of numbers. All right. Thanks, Daniel. Any other questions
Thank
I can help you with?
No, I was just confused why it was blowing.
No worries at all. Hope you have a
good
nice
one.
day. All right. Bye.